Have you ever had a word right on the tip of your tongue? Now, imagine that feeling, but for almost every single word. The thoughts are there, clear as day in your head, but you just can't get them out. Today, we're diving deep into the mystery of aphasia, a condition that has forced us to completely redraw the map of language in the human brain. Just listen to this for a second. This is someone trying to describe a simple trip to the hospital. You can hear it, right? The effort, the struggle. The core ideas are all there. Dad, hospital, doctors, the days of the week. But connecting them into a smooth sentence, it's an incredible challenge. This is the raw human experience of something called expressive aphasia. So, what on earth is going on in the brain here? Well, this is expressive aphasia, sometimes called Broca's aphasia. It's when someone loses some of their ability to produce language. But, and this is what's so fascinating, their understanding, their comprehension is often totally fine. They know exactly what they want to say. It's like the bridge between the thought and the spoken word has crumbled. And this creates some really distinct patterns. Their speech can become halting, you can just hear the effort. You often get what's called telegraphic speech, like an old school telegram message. It only has the most vital words: dad, hospital, teeth. All those little connecting words like the, is, in, they just get dropped. And honestly, the heartbreaking part is that patients are usually painfully aware of their own struggles, which, as you can imagine, is incredibly frustrating. Now, to really get what's going on, we need to take a step back and look at the old map of language in the brain. This was a story that dominated neuroscience for over 100 years. The whole story really kicks off back in the 1860s. There's this French neurologist, Paul Broca, and he's studying patients just like the one we heard. After they passed away, he'd look at their brains, and he found damage in the exact same spot, over and over again, a little region in the left frontal lobe. A decade later, another guy, Carl Wernicke, finds a different spot, this time in the temporal lobe, that's linked to understanding language. For the next century, those two spots were basically the entire language map. And this led to a theory that was, it was beautifully simple. The idea was that language was just a two-part system. You had Broca's area, which was the speech factory. Its job was to make the words. Then you had Wernicke's area, the comprehension department, which was for understanding them. Simple, neat, and for a very long time, it seemed to explain everything perfectly. This whole thing was called the Wernicke-Geschwind model, and it basically works like an assembly line. An idea pops up in Wernicke's area, it travels down this one nerve fiber highway called the arcuate fasciculus and arrives at Broca's factory to get put together into words. Then boom, it gets shipped off to the motor cortex so you can actually say it. It was a very linear, very mechanical process. But here's the thing. As neuroscientists got better tools, new ways of looking inside the living brain, this simple, tidy little map, it started to fall apart. The evidence just kept piling up, and it forced researchers to ask this really radical question. What if this map we've been using for 100 years is just plain wrong? The cracks started to show everywhere. For instance, patients with damage in the so-called production area also had trouble understanding grammatically tricky sentences. And patients with damage in the comprehension area would say things that were grammatically perfect, but made absolutely no sense. Those two neat boxes were bleeding into each other. But the real nail in the coffin? Modern brain imaging. When we could finally watch a living brain work, we saw that even simple language tasks lit up the brain like a Christmas tree, way, way beyond just those two little spots. And yeah, the verdict from modern science is crystal clear. As these researchers put it back in 2016, the classical model is now obsolete. It was a good first draft, an essential first step for sure, but it was time to draw a whole new map. Okay, so what does this new map actually look like? This brings us to the modern way of thinking, a model often called the MUC model. The biggest, most fundamental shift is this. Language isn't happening in two little factories in your brain. No, it's a dynamic, spread out, deeply interconnected network of regions all talking to each other. And this image right here shows the new idea perfectly. This is the MUC model. So instead of a production center and a comprehension center, language is broken down into three core jobs or functions. You've got the memory component in yellow, mostly in the temporal lobe. Then there's unification in blue, centered right around Broca's area. And finally, in pink, you have control up in the prefrontal cortex. So let's quickly break that down. The memory component is basically your brain's dictionary and grammar rulebook. It's where you store all the building blocks, words, sounds, how sentences are supposed to work. The unification component, right around Broca's area, is the construction crew. It takes all those building blocks from memory and actively combines them into sentences. And finally, the control component is like the project manager, helping you take turns in a conversation or pay attention to what's important. This is the biggest takeaway right here, the brand new job description for Broca's area. It's not just a production factory anymore. It's a unification hub. Its job is to pull pieces from memory and weave them together into bigger structures, like sentences. And here's the kicker. It does this both when you're trying to talk and when you're trying to understand what someone else is saying. It's doing double duty. And this new network model is totally backed up at what we now know about the brain's wiring. That old idea of a single highway connecting the two spots, that's gone. As you can see, modern imaging shows us this incredibly complex web of pathways connecting all the language regions. In fact, you can see how much more complex these connections are in human brains compared to chimps or macaques. That extra wiring might be exactly what makes our kind of language possible. So, we've gone from this simple two-box idea to a complex three-part network. So what? Why does this new view actually matter? Especially for patients dealing with aphasia. Let's just really nail down this shift in thinking. We've gone from seeing Broca's area as a simple assembly line for speech to seeing it as a dynamic unification hub. Think of it more like a collaborative workspace where different pieces of information are brought together to create meaning. And that workspace is critical for both speaking and understanding. And this network idea finally helps make sense of the real-world messiness of aphasia. If language is a network, then brain damage isn't like shutting down one factory, it's more like snipping wires on a complex circuit board. Hitting one spot, one connection, can cause all sorts of different problems and affect multiple skills at once. It just explains what we actually see in patients so much better. So you see, this isn't just about drawing a new map in a textbook. It's a whole new way of thinking about one of the most fundamental human abilities. If language isn't just a place in the brain, but a distributed network, what does that mean for how we learn? For how our brains can recover from injury? What does it even mean for how we think? The implications of this are huge, and we're really just beginning to figure them out.